This is the third and final part of Lesson 10.11, Lagrange error-bound inaccuracy. In this part, we're going to look at two more examples. The first one is dealing with alternating series. So we're going to start by a note. If an error calculation is required on the AP exam, all your work must be shown, so the calculator can only be used as a method to check your computations. So all the work we've been doing has to be shown. You can't just plop some numbers in a calculator and say it doesn't work. So you want to make sure you're showing this work. So for number 4, we are to use a Maclaurin series for y equals e to the x to estimate 1 over the square root of e accurate to 4 decimal places. So what we're going to do is start by writing our Maclaurin series for e to the x and then change it so it works for 1 over the square root of e. So just to review, e to the x is the summation n equals 0 to infinity of x to the n over n factorial. So if we are to do 1 over the square root of e, that is really e to the negative 1/2 power. So that series then is going to be adjusted in this way. So we're going to have negative 1/2 to the n over n factorial. And this turns out to be an alternating series when we write it this way. We can pull out that negative 1. And then we have 1/2 to the n over n factorial. So now what we have here is an alternating series. I don't know why I can't make an n here. Sorry about that. Alternating series. Okay, so what we want to show is, we can do this now, we can say that the error has to be less than or equal to the first unused term. That's the idea we're going to use for the error bound. So we want this to 4 decimal places. So let's do a 5th degree polynomial and see where we are there. So p sub 5 of x, well, we're doing it at 1/2. So let me put the 1/2 in there. Our x is 1/2. So this is going to give us 1 minus, and then we're going to have 1/2 plus 1/2 squared over 2 factorial minus 1/2 cubed over 3 factorial plus 1/2 to the 4th over 4 factorial minus 1/2 to the 5th over 5 factorial. And I just realized I wrote this as a 4. Okay, and so if we want to be accurate to 4 decimal places, what we're going to have is, so I just started writing our terms out here. We're going to have this. We want 1/2 to some power k, I'll call it, over k factorial has to be less than 2, 3, 4 decimal places like that. So that's why I'd used n equals 5. Now I could be off, so I'm doing that. So what I want to do then is let me just double check what the 6th one would be. So in case I have to write another one. Let me see what my sixth coefficient would be. So it would be 1/2 to the 6 over 6 factorial. If I put that in my calculator, this is approximately equal to 0.0000217, which is, very small, which is what we want. So fifth degree works. So we are going to use the idea that p sub 5 of 1/2 is approximately equal to, and that's going to come from this polynomial, 0.6065104, and the actual value of e to the negative 1/2. I check this in my calculator, is 0.6065306, which is pretty close. So this is what I'm talking about with your calculator, is the idea that you could have just checked this in your calculator and checked this to see how close they were. But what they're looking for is for you to do this work here to show that what you have is an alternating series, that you have going to use the first unused term, and that the error has to be along this order right here. So, and then you can check it. Okay, this is our final example. So using the Maclaurin series for cosine of x, which is another alternating series, write the fourth degree polynomial and use it to compute cosine of pi over 12. So cosine, let's just start by writing that one. Cosine of x is a Maclaurin series, can be written as the summation of n equals 0 to infinity of negative 1 to the n times x to the 2n over 2n factorial. So it catches all the even terms. So a fourth degree polynomial doesn't mean n is 4. It means we want x to the fourth. So we just have a few terms here. So we have 1, the first term, minus, when we put 1 in, we get x squared over 2 factorial. And when we put 2 in, we get x to the fourth over 4 factorial. So that's the fourth degree polynomial. So we're good there. So now we're going to use that to estimate cosine of pi over 12. So we're going to have 1 minus pi over 12 squared over 2 factorial plus pi over 12 to the fourth over 4 factorial. So this is approximately equal to, it's almost 1.965926, and it's actually pretty close to the real value. The real value is 0.965926, and so those digits all line up, which is pretty good. So use the Lagrange error bound to show that the absolute value of f of pi over 12 minus the polynomial, the fourth degree polynomial pi over 12, is less than 1/5000 on the interval 0 to 1. So again, we've done this for sine. We can say that our maximum value for cosine is going to be 1, because that is cosine's upper bound. And we want to remember that what we're looking at here, when we have f of pi over 12 minus the fourth degree polynomial pi over 12, that is our error. So this has to be less than or equal to our m over 5 factorial times x minus 0 to the 5th power. And our x is going to be pi over 12. So this is our fourth of x. And this is going to be less than or equal to 1 over 5 factorial times pi over 12 to the 5th. And this is approximately equal to 1.0248 times 10 to the negative 5. And 1 over 5,000 is equal to 0.0002. So our error is definitely less than, so our R4 of x is less than 1 over 5,000. So we have shown that this is true. So that, I wrote that, that's not the best way to write that. Let me put it this way. R4 of x is equal to, so we are actually answering the question given. Sorry, that was a little sloppy. It's less than or equal to 1.0248 times 10 to the negative 5, which is less than 1 over 5,000. There we go. That's a better way to write the answer. So now what we're supposed to do is use the 4th degree Taylor polynomial for cosine about x equals 0, which is our Maclaurin, to find an approximation from cosine of 0.8 and determine the accuracy. So it's very similar to the first couple parts. So cosine of x is going to be, I'm going to use a t this time because we're using Taylor, t4 of x, which is what we found before, which is going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And so cosine of 8/10 or 0.8 is going to be approximately equal to our Taylor polynomial at 0.8. So we have 1 minus 0.8 squared over 2 factorial plus 0.8 to the 4th over 4 factorial. So we get 0.697066. And we want to determine the accuracy. So since this is, again, an alternating series, what we can do is say that our error has to be less than or equal to the next term. And that next term is going to be there's different ways we can write it, so I can just do this since I'm using a calculator. That's a 4. So that is another way to say our error. So this is going to be less than or equal to, the next term would be 0.8 to the 6th power over 6 factorial. And that is approximately equal to 0.000. Those are zeros. They're terrible looking zeros. I'm trying to look at the number on my paper. 0.00345. That's enough. That's enough decimal places. Okay, so now we're again trying to show that, again, a boundary for our error. So what we're going to do is we're going to take what we got as an answer in part A. I'm sorry, we're in a different problem now. In part C, the first part, this answer right here. And we're going to add and subtract our error here is what we're going to do. So we're going to do 0.697066 minus, I'll write all the digits here, 3408 is less than or equal to cosine of 0.8, which is less than or equal to 0.697 0.066 plus our error, 0.003408. And when you do those calculations, you get an interval of 0.697025 0.69743075. So that's the answer to the last, whoops, I meant to hit the highlighter, the answer to the last part. And that's the end of this lesson. If you have any questions, please feel free to ask them.